Okay, now in the last video we looked at linear approximation, and so in this video we're going to look at approximating a function near a point with a quadratic function. So again, let's say we're looking at the graph of a function f near a point a comma f of a, and now we define the first Taylor polynomial p1 of x to be the tangent line of this blue curve at the point in red. That's what you see here in green. Okay, and so now we wish to find the quadratic function that will, in some sense, best approximate the blue curve near this point. Okay, so graphically we're looking for the parabola that will pass through this point and will provide the best quadratic approximation to this blue curve near this point in red. Okay, so what are desirable properties of this quadratic function? I'm going to call that p2 of x. Okay, well, again, we want the graph to pass through the point a comma f of a, and so that would imply that p2 of a is equal to f of a. Now, we'd also like the slope of this parabola to equal the slope of the blue curve at this point in red. So in other words, p2 prime of a should equal f prime of a. And then lastly, since we're working with a parabola, right, a degree 2 polynomial, we can also look at the second derivative, or in other words, the concavity of this parabola. Okay, so we're also going to require that the concavity of this parabola at this point in red is equal to the concavity of this blue curve at this point in red. All right, so that says that the second derivative of p2 evaluated at a is going to equal the second derivative of f evaluated at a. All right, so from these conditions, we arrive at the following definition for the second Taylor polynomial based at a. Okay, p2 of x is equal to f of a plus f prime of a times x minus a plus f double prime of a divided by 2 factorial times x minus a squared. Okay, so I want to make a few comments about this definition. The first thing to note is that these first two terms are nothing other than just p1 of x, right? And that's just because if you look at these first two conditions on p2, those were the exact conditions on our linear function p1, right? We wanted the line to pass through that point and to have the same slope, and that's what led to these two terms, right, giving us the definition for p1. So these two conditions on p2 then mean that the constant and the linear term for p2 will be the same as that of p1. And now we're just tacking on this quadratic term, okay? And you might wonder, well, first, why am I writing this as 2 factorial? Well, as we'll see when we look at higher order approximations, a nice pattern emerges with these factorial terms down in the denominator. Okay, so that's why I'm writing it this way for now. Okay, the other thing I want to note is that if I look at the second derivative of p2, well, what am I going to get? Well, the derivative of f of a is 0, and so its second derivative is certainly 0. The second derivative of this linear term is also 0, because if I differentiate twice, I'm going to get 0, right? Because the first derivative is just f prime of a, because I'm really just differentiating x minus a, and then differentiating again, I'll be differentiating that constant, since that's 0. So then it's up to this term, right? Now if I differentiate once, I'll get 2 times x minus a, right? Because this coefficient in front is just a constant. And notice that 2 in front will divide out with this 2 down in the denominator. And then if I differentiate it again, well, I'm just differentiating x minus a. That'll give me a 1 times this second derivative. And voila, there you go. Okay, so now the whole idea here, right, is we're looking to construct this quadratic function that's going to give us good approximations to this blue curve near this point A. Okay, and this type of approximation we call a quadratic approximation. All right, so now what I'd like to do is look at part A on the worksheet. So it says, compute the second Taylor polynomial for each function at the specified point. Then use this polynomial to approximate the function at certain values and compute the absolute error in each approximation. And so here we have f of x is e to the x, and a, our base point, is 0 in this case. And here I'll bring up the definition again of P2. So what we need to compute is f of 0, f prime of 0, and f double prime of 0. Okay, so those are all right here. Since the derivative of e to the x is just itself, we have that the second derivative of e to the x is also itself. And so all of these values, in fact, come out to be 1. And so putting those together in the definition, okay, we get that p2 of x is 1 plus x squared over 2. All right, I'm going to go to a graph here to show you what this looks like. So here in blue is our exponential curve, e to the x. There is p1 of x. This is what we saw in the last video. That's the tangent line to the exponential curve at the point 0, 1. And then for p2 of x, right, our parabola, this is 1 plus x squared over 2. And as we can see, right, since this parabola can bend, right, think about bending a wire to try to fit the shape of this blue curve, right? Well, it certainly looks like it's doing a better job in approximating the blue curve near this point 0, 1. Certainly looks like it's doing better on a wider interval than the green line is, right? So keep that in mind. Now let's go ahead and approximate the value e to the 0.05. So for that, right, just first note that e to the 0.05, that's just f of 0.05. So that's approximately p2 of 0.05. And if I plug 0.05 in for x into this expression we found for p2 of x, we get 1.05125. Okay, now if I look at the absolute error in this approximation, that's just looking at the difference between the exact value, e to the 0.05, and our approximation. And that absolute error here is quite small. It's 0 point, and then there's 4 zeros, and then 2 1s, 096, and so on, okay? So that's a lot better than our approximation from in the last video, right? So if you go back to the graph, okay, there is the point, and I'll take out the, or I'll leave that in for now, I guess. There's the point we're looking to approximate on the blue curve. And there is the point on our parabola in orange. And as you can see from that starting view, can't even decipher them, but if I start to zoom in, you can see there is a little gap, but looking at the scale, right, that gap is quite small. Okay, so it's giving us quite a good approximation. And again, look at the difference between the orange parabola and the line on this view here, right? You can see there's a considerable gap, right? At least relatively speaking on the scale. All right, so let's now go to part B. All right, so we're looking at f of x is cosine of 2x, and here a is pi over 4. So we'll start out doing the same thing. I want f of pi over 4, f prime of pi over 4, and f double prime of pi over 4. And so f of pi over 4, that's the cosine of 2 times pi over 4. So that's the cosine of pi over 2, and that's 0. Now for f prime of x, don't forget the chain rule. It's going to be negative 2 times the sine of 2x. So plugging in pi over 4, we get negative 2 times the sine of twice pi over 4. So that's negative 2 times the sine of pi over 2. And so that's equal to negative 2. And then for f double prime of x, okay, again, don't forget the chain rule. Note we get a cosine term again. So that leads us to negative 4 times the cosine of pi over 2, which is equal to 0, right? That's our value for f double prime at pi over 4. And so now putting all that together in the definition from p2 of x, right, we get that p2 of x is, in fact, linear, right? It's negative 2 times the quantity x minus pi over 4, right? And it's linear because the second derivative term is 0, right? So this part right here, the quadratic term, actually just drops out. All right, so what's going on there? You might say, wait a minute, I thought p2 of x was supposed to be a parabola. Well, if we look at the graph of the cosine curve, at the point pi over 4 is 0, okay, we are at an inflection point for this cosine curve, right? There is p1 of x, the tangent line to the curve, at this point in red. p2 of x, then, is really the same thing as p1 of x. And the reason why is because we're at an inflection point. And see, inflection points are places where the second derivative of our blue curve vanishes. That's what's going on there. All right, so now let's go ahead and approximate the value of cosine of 2. Now note that if I want the cosine of 2, I want to plug in 1 for x. So we're really looking to approximate f of 1. So that's going to be approximately at p2 of 1. So if I plug in 1 for x into what I just found for p2 of x, I get negative 2 times the quantity 1 minus pi over 4, which is about negative 0.42920, blah, 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 blah. Okay, so here on the graph, in blue, that's the point we're looking to approximate. And there's the corresponding point on the, well, p2 of x. Not parabola, in this case, is actually a line, but that's the corresponding point on p2, and we can see, yep, the gap looks more sizable there. If I look at the absolute error in this case, between the exact value and our approximation, it's about 0.0130, blah, blah, blah. All right, so that does it for this question. Now, in the next couple of videos, we're going to just look at extending this idea, right? We started with linear approximation. Here we're looking at quadratic approximation. So we, of course, could do cubic approximation, right, with degree 3 polynomials, and then quartic approximation with degree 4, and then degree 5, and so on. Okay, so that's where we're headed with all of this. All right, well, I'll see you in the next one.